density to be measured. And the first attempt to describe this recombination was using Saha equation. So if the universe was in thermal equilibrium during this process, we can calculate this number density of every electron using Saha equation. As you already know, probably this is by this combination, and this E naught is ionization energy of hydrogen. But we know this is not true. So to more accurately describe this process, we need more physics we have to consider. And I think in 1960s, James Peebles came up with some model, which now we call Peebles 3-level atom model. And situation is following. So let's say these are energy level of hydrogen. This is ground state and first excited state, and so on. First important thing is the direct recombination to ground state. This process is very inefficient because this process will emit photon which has this amount of energy, and it can immediately photoionize the other neutral hydrogen. So this is very inefficient process, so we are not gonna consider this process. And once electron and proton recombine and form some high energy excited hydrogen state, and this state can decay to first excited state in a very short time scale compared to expansion of universe. So, and if we also disclose this decay is instantaneous, that is what people call as big recombination. And this is described by SB recombination rate alpha b, which is just sum over all the recombination rate to any excited state. And we can, once they form a first excited state hydrogen, it can also be photoionized, and that is described by this photoionization rate, which can be obtained by detailed balance argument. So if I describe how this first excited state changes, then this will be whenever proton and electron meet, they will form first excited state with this rate, and there will be also photoionization proportional to number density of first excited state, and these polar rate should be 0 when they are in thermal equilibrium. So this beta B can be obtained in this relation to our equation times recombination rate. So we use these two rates in this model, and there is, and more importantly, once they form first excited state, there are two channels they can decay to ground state. One is from 2p state and this process is characterized by Lyman alpha escape rate. So once 2p state decays to ground state, there will be Lyman alpha photon, and this photon will excite this ground state to first excited state again. But due to the expansion of universe, this photon, Lyman alpha photon, will be redshifted. So, and at some point, this photon will escape without re-exciting this ground state. This is the rate of that process. And there is another channel, one more channel. From flat state, there can be also two photon decay, and this is characterized by this two photon decay rate, lambda. And although this atomic process is much faster than expansion of universe, so we can assume, or we can use steady state approximation for this first excited state number density. And what we end up with is, if we use all these facts, we end up with this equation for free electron number density.
But if you use equilibrium everywhere, you will get just Saha, correct? So the question is where exactly you depart from equilibrium. You agree, right? If you make steady state for all your kinetic equations, the result will be just the Saha equilibrium.
Oh, I'm using steady state approximation only for this N2 state, because whenever we form, or whenever they form excited states, they will decay very fast to this first excited state. But this process is kind of bottleneck to form this ground state.
So which one is the slow process which can compete with the expansion of the universe, right? That's the question. If all your processes are faster than the expansion of the universe, then you will just get Saha. There must be some process which is so slow as to compete with the expansion rate of the universe. Otherwise, you just get Saha equilibrium, don't you?
All right, maybe I said. Then I guess this process should be comparable to Hubble.
This two photon decay or what?
These two, both are comparable, both rate. Is it?
What's the two photon decay rate, more or less?
8.22%.
And what's Hubble? What's the age of the universe at that time? It's not 0.1 second, right?
Right. Then I'm a bit okay. I want to know this. Yeah, these rates are.
So these rates are fast compared to Hubble. So the excited state is very quickly adjusting its population to the ground state or the continuum fraction. But then Nanoom is going to write the evolution equation for the continuum for the free electrons, and that is slow. So you have three levels.
So radiative equilibrium is really equilibrium, but
Sorry?
some radiative equilibrium you are saying is equilibrium.
I'm saying that the middle level, n equal 2, adjusts to the other levels very quickly, but the overall population of ionized hydrogen, this adjusts slowly. This varies on a Hubble time scale or slower.
But which reaction is slow? Right, you have a chain of chemical.
The recombination rate is comparable to.
Recombination rate is
Yes.
slow, right? Okay.
Yes. Once you adjust for this P-Boltz factor.
So these radiative transitions are all fast, but the recombination is
Yes.
slow.
Yeah.
Okay.
Then if I continue, this is recombination rate to first excited stage, but we need one vector C here, which we call Peebles C vector. And this is given by, let me write. So this what C implies is probability of this first excited state to decay to ground state before photoionized. And we have one more term here, which so early time is beta dominant. So this effect becomes very small. I think so that will answer your question. So yeah, this is famous Peebles free-level model. But people realize this Peebles model is not accurate enough for Planck data. So what people actually have to do is we have to include large number of, let's say n, large number of energy shells of hydrogen. And if we have these n energy shells, we will have n times n plus 1 over 2 energy state. And which means, and for Planck, we need at least 100 energy shells, which means we have 5,000 equations to solve to describe recombination history accurately. But this is computationally very expensive. So what Yajin and his advisor Hirata came up with this new model, which we call effective multi-level atom model. So in this case, unlike Peebles model, where this recombination rate determined by simply sum over the recombination rate to excited state, we calculate, for example, effective recombination rate to 2p state and 2s state by considering, in addition to bound free transition and also possible bound transition.
Sorry, Nanoom, wasn't there some Bulgarian guy at Harvard who spent his life solving this recombination fast or something it was called? What was his name? This guy.
Is it Sasanov? I don't know if his
Sasalov, exactly.
Yeah. Yes.
Right? Is it more or less the same?
Yeah, but there's a, I mean, we can discuss it, I can explain it.
But it's the same, right? Idea,
Not the
right?
same, no.
Not the same?
They did some numerical calculation and then they fudged some result and even their numerical calculation.
So you are doing more first principle.
Yes.
Okay.
Are there codes that slowly do the 5,000 equations?
Sorry?
Are there codes that
No,
slowly
and
do
actually
step 3?
Sasalov they did not do so. Sasalov they only resolved the n levels and energy shells without resolving the angular momentum states. So they did not fully account for angular momentum substates. We account for the angular momentum substates, and then we show that we can reformulate the problem to get the exact effective recombination.
So you will beat him.
But I was wondering, has anybody done like the stupid slow way?
Yeah, of course.
Yeah,
Of course, this was the whole point that people were taking days to calculate one single thing.
I see. That's what you
People actually did this calculation, but it took so much time. That's why that is motivation of this model. So we can just calculate this effective multi-level, this effective recombination coefficient, or also recombinate effective photoionization coefficient, which is only function of 2 temperature. Which means that's why we can pre-calculate this coefficient and tabulate it and use in the code. When we even when we have different cosmology, that's what we do.
So let me ask, what are the kind of expansion parameter here. How to estimate, because you're doing some approximation, but how to approximate estimate what is the uncertainty of this calculation or the next order correction? Is there really consistent expansion here?
I don't think there's an analytic or a clear way to show it besides numerically. You double your cutoff, your truncation n, and then you check that your results don't change. But I don't think I can give you a clear, explicit way to show.
That's for this item 3, right?
Sorry?
That's for this approach with truncation to 100 thing.
Yeah.
But then you're doing something different. Than
No, this is a reformulation of the problem that still has, you still have to compute some large, solve some large system of equations, but you just do it once and for all. And then you compute some atomic physics functions rather than solving a time evolution problem. But yeah, the convergence, you just have to do it numerically. Like, you have a system of equations that you have to truncate at some point. I don't have a very strong argument to tell you why it's which point you truncate it.
And if I add, this is actually a function of the number of energy shell, but this is, but if I plot this quantity as a function of n, it looks like it converges to some value with a large n, and we just extrapolate to use it. And with this model, we can calculate recombination history in a very short time. But there is another important element we have to consider. There is original radiative transfer effect, which can be important in sub-percent level. For example, there is frequency diffusion in resonance scattering in Lyman alpha, and also we have to take into account higher Lyman line transition and also feedback between them. So, for example, if we have some Lyman alpha photon emitted by Lyman alpha transition, while universe is expanding, this photon will be redshifted, and at some point you will have some similar energy or same energy as Lyman beta photon, so it will impact the Lyman beta transition. So this kind of process should be considered by solving radiative transfer equation. And combining these two, we can calculate recombination history very accurately. So the estimated theoretical error is order of 10 to the minus 4. And this is what IREC, which is code, recombination code developed by Yashin, and also Cosmological, which is developed by Jens Schulba. These two codes these two are what these two codes do. But and there is another code which called breakfast. This code is based on Peebles model, which is not very accurate. So they implement some correction, constant correction, to reproduce this result, the result of IREC and Cosmological. So some constant. So one correction is constant Hodge factor F, which is multiplied to this case B recombination rate alpha B to accelerate recombination.
Why does that work? Like naively, the correction you need to apply would be lambda CDM parameter dependent.
That's actually one of the motivation of our improvement. So this is just constant factor, and there is also constant correction function to some Lyman alpha escape rate. But somehow it works very. I think they actually implement that correction to reproduce this result at the lambda CDM cosmology
But I
best
thought,
fit.
I thought this correction is actually used for comparing a Planck data.
Yeah,
Planck
this code is
itself.
actually, this code is mainly used for Planck
So
analysis.
it's surprising to me that it works.
Yeah, that's
Up to
actually
the
what we
precision
found.
they need.
Yeah. So, as you said, this is not physical correction. This is not cosmology dependent, so it kind of doesn't make sense to me to use this correction. So what we did to improve, and there's one more motivation. So this code takes around half second to run, and this request takes only 20 milliseconds. I think this is also one reason why people keep using this request, even though this correction is not critical. So what we did is we wrote new version of HiREC, which we call HiREC 2. This is based on same effective multi-level atom model, but we introduced some kind of correction, but which is cosmology dependent correction. So, and the big difference between this running time is mainly due to solving this radiative transfer equation. But we wanted to avoid solving this equation to make it fast. That's why we introduced some correction to Lyman alpha escape rate. But their correction was just constant, but our correction is cosmology dependent. And what we found is the difference between HiREC, original HiREC, and request. This was order of 10 to the minus 2 or 10 to the minus 3, depending on redshift. And difference between HiREC and HiREC 2 is order of 10 to the minus 5. And also, our new code has runtime less than 1 millisecond.
So the thing that Planck was actually doing was wrong by 10 minus 2 to 10 minus 3.
But yeah, but we checked that. So we thought this request could induce some bias because due to this simple correction to their calculation, but it turns out in, let's say, in the whole region of 9.7% of confidence region currently allowed by Planck, in that cosmology, this request actually doesn't induce any bias. But it can be the case when we consider next generation of CMB. There was motivation of writing this new code. But yeah. But I was kind of surprised that this simple correction works very well, even though it's not physical. That's one thing we found. But anyway, our new code is effectively has same kind of order as original HiREC code, and also it's much faster, even faster than request. So, and now this code is implemented in two commonly used Boltzmann code Kemen class.
So what made it faster? There's some physics idea there?
Actually, there is no very interesting physics when in this improvement. So what we do is we define we define our correction delta to inverse over Lyman alpha escape rate, and we solve for this delta to reproduce original high-rec result. Then we have this delta. So this is just kind of what we did is kind of similar to what Blackfast did, but the main difference is our correction is cosmology dependent. And why we have such a small runtime is when we have to solve solving this equation takes time, and also it requires some minimum step size to solve. There is some limitation to, you cannot have some arbitrary small time step when we solve this Reddit transfer equation. But in this case, since we don't solve this equation, we can have a smaller time step compared to high-rec or cosmology. That is one reason why we achieved this small runtime. And so all of this, I'm only talked about recombination history in background cosmology, but in the next half, Trey will talk about each perturbation and application.
So cos can also be used to get the ionization rate versus the ratio. So what's the error between the cos and the
So can
cos code? The cos. I mean,
can you repeat? I didn't.
I mean, cos can also produce the high ionization rate.
Plus uses those codes.
Oh, use this.
Plus.
Are you in class? Oh yeah. You can choose, these Blackfast and also high-rec 2, these are implemented in class. You can choose just between these two to calculate.
Can I ask quickly again about the speed up? I mean, it's amazing that you can be faster than RecFast, right? Because RecFast is just solving a differential equation. You're solving the same differential equation with more stuff, and somehow you can beat RecFast. I mean, that's
Right,
amazing.
Right. That's a good question. So when I wrote this number, this is using default time step of RecFast.
I see.
And actually I haven't checked in detail, but if I can reduce time step of RecFast to achieve this number, but that might be a good thing to check. But in my case, I think we have higher order differential. We have a higher order differential equation evolve in our code. There might be one reason we have sugar.
I think it is, there is a higher order for the solver, so you can take larger steps while maintaining the same accuracy.
I see.
But I haven't checked if that's possible also with it.
So I suggest we move to the second half and people can ask questions to both at the end. True. We'll clap at the end. There's one talk. There's one title.
The classical music, which is clapping between these.
Yeah, exactly. It's like two movements. Yeah.
All right, so now that Nanoom has introduced recombination and the physics that go into that, I'm going to talk about perturbing recombination. But before I go into talking about perturbing, I'm going to do a little pedagogical review of recombination that probably all you know, but I'm just going to go through it anyway for completeness. So first, I'm going to talk about how recombination results in some observable, and the observable I'm going to talk about is the CMB, the cosmic microwave background radiation. So first, I'm going to draw a little snapshot of shortly before recombination, where I'm just going to take some slice. Before recombination, everything is a plasma, and in this little slice, I'm going to draw some plasma here, whatever. The temperature, the global temperature of this plasma, I'll write as T global, is effectively greater than the ionization energy of hydrogen. That's because it's before recombination. So when you have an ionized plasma, if you emit a photon, it's going to be scattering so frequently with the electrons, it's dense enough that the photons are going to scatter so frequently. Actually, It's going to scatter so frequently that you effectively have the photons locked into place. So essentially, we'll have a baryon photon plasma. So this is before recombination. Another phenomenon that's happening beyond this global temperature, there are also density perturbations or temperature perturbations coming from inflation, stretching quantum fluctuations out. And so you actually, beyond this global temperature, you'll have hotter regions. Let's just assume that we're going to do some plane wave oscillation of temperature here. So we'll have some characteristic scale here. K -1, here, this, of some plane wave temperature where these more densely chalked places are hotter temperatures and these are cooler temperatures. And when you have these types of density perturbations, these temperature perturbations, you're going to have, because of density perturbations and dark matter potential wells, the matter is going to start falling in. But then, because we have a baryon photon plasma, the photon pressure is going to be pushing out. And so you're going to have some oscillation. It's going to get denser and denser and hotter, and then it's going to start pushing out and getting cooler and cooler. So these temperatures, the cold and the hot, actually are oscillating back and forth. And this is called baryon acoustic oscillations. And this is important for the CMB. So this is a picture before recombination. Let's talk about what happens during or after recombination. During/after recombination. So the global temperature here is going to be less than the ionization energy of hydrogen, and it actually turns out to be a lot less than, because the photon bath is so plentiful that even if you're a lot less below the ionization energy, in the tail end of the distribution, you're still going to be ionizing everything. So eventually, once we're much below this energy, hydrogen is going to recombine. So we're going to have electrons and protons going into neutral hydrogen. And we still have these types of baryon acoustic oscillations. It's going to be at a different phase than this oscillation because it's at a different time, but we generally have these acoustic oscillations still going on. Now, what is important now that hydrogen's recombined is that if you emit a photon, depending on the energy, if you're at low enough energy, which we are in this case for the photons that are emitted here, photons are going to effectively see this as a neutral background. And so during recombination, as things are combining, we'll have a photon that emits and maybe scatters for a little, or propagates for a little bit, and it scatters again, propagates a little bit, scatters again, and then streams forever. Let's do a couple more. We have the scattering, streams, and we have some scattering, and then it streams. Now, as recombination is happening, these photons are scattering on different temperature fields and encoding more information about the CMB or the baryon acoustic oscillations, such that once they finally free stream, let's say that we're positioned here, so this is us, what we see are different temperatures in different directions. And so the important thing to note is that photons are imprinted by BAO. Now, the reason why I went into all of this is to talk about perturbations. And so the actual statistic or the information that comes from these CMB photons reaching us is the CMB, as I had mentioned. And we generally measure the CMB through statistics or correlations between temperatures in different directions. But one thing that is important that I want to emphasize is that baryon acoustic oscillations is time dependent, such that if you do change when this recombination happens, you're going to see a different CMB. So I want to emphasize that the CMB coming from this picture is very dependent on when recombination happens and its rate. The rate is important also because as it's gathering information from the baryon acoustic oscillations, if it's longer, you're going to start smearing out more of that information. So what I'm saying is, because it's very dependent on the time and on the rate, if we perturb this recombination, then we're going to see a change in the CMB. And that's kind of the stage of perturbing recombination. So just to talk about perturbing recombination and what things could perturb the recombination, one thing I actually want to mention before I talk about that is the CMB is actually very well predicted by a lambda CDM model and some single field inflation. It's predicted so well that if you do perturb recombination, you can see that the data might not match a new theory that perturbs recombination. Therefore, it's going to be very, very constraining when you have some beyond the standard model that's perturbing recombination. So if we introduce some beyond the standard model idea beyond lambda CDM, some of those ideas could just be dark matter decaying or annihilating, somehow dark matter interacting with the standard model. What Yasin and I are more interested.
Sorry, Trey, can I ask you? But even before you go beyond the standard model, in the standard model, the way you have described it, perhaps doing perturbative recombination is important. Was it done, and is it seen?
Right. So you're talking about going beyond like perturbations of just.
Exactly, right.
Yeah. So.
Because the way we do the cosmological perturbation theory, at least the way I know, that it ignores perturbative recombination.
Right. So yeah. So,
rightly so or not?
No, that is true. So when you actually get the CMB, you're solving this Boltzmann Einstein differential system that you solve perturbatively, and you go to first order in terms of like density perturbation.
Well, they do it perturbatively.
Yeah, they do it perturbatively, but they only go to first order. And if you go to, and some codes actually, or some people go to second order, going from the fact like that you have some baryon velocity that's interacting with some baryon overdensity. This will have a different Thompson scattering is kind of the idea here. But if you go to second
one actually has to do it, it is something observable.
So I believe it's too small to be observed because you have two orders of the primordial curvature perturbation here. And so, but that's actually a really good question because the beyond the standard model things I'm going to be talking about is going to be something that goes to higher order in perturbation theory. But the idea is that there's no reason a priori that these models shouldn't be actually a very strong effect on perturbation at second order. But I'll get more to that soon. So just to give you some other beyond the standard model ideas that might perturb recombination is dark matter somehow interacting with the standard model. Something that Yasin and I are interested in are primordial black holes, which are black holes that would have formed shortly after inflation and would exist throughout cosmic time. And these primordial black holes can either evaporate through Hawking evaporation or radiation, or they can accrete. And Yasin and I have been inspecting the accretion. Another idea, exotic idea, is cosmic strings, which I won't go into too much detail about, but these are just some ideas in some ways to perturb recombination. Now, how these actually perturb recombination, at the end of the day, for these cases, they're somehow going to be injecting energy into the primordial plasma. So they can inject energy. They inject energy. They're going to perturb recombination, and then ultimately going to give us a different CMB, as I had mentioned. Now, how do you inject energy? These can just be through photons. It could be through electron positrons. It could be through anything that's just some energetic particle that's somehow interacting with a standard model. How you can perturb recombination? Well, first off, it could perturb the free electron fraction that Nanoom was talking about, but the global one, so averaged over space. And it can also perturb the matter temperature, which is also important for recombination. And then these types of changes, these global changes, which is what's generally inspected for these types of problems, this will change the CMB at the power spectrum level. And when I say power spectrum, I mean the Fourier transform of the 2-point correlation function between temperature fluctuations, where theta, sorry, this is a little bit messy. Theta is the change in temperature over some mean temperature. Now, the thing that Yasin and I set out to understand is, what if we're not just injecting energy homogeneously, we're not just going to affect this global signal, we're going to inject energy inhomogeneously. And if we inject energy inhomogeneously, then our changes to the free electron fraction are going to depend on space as well as matter temperature. Now, the thing that's unique about this inhomogeneous energy injection is that you're not only going to affect the power spectrum, but you're also going to affect higher order statistics, such as the bispectrum, so the 3-point correlation function, or even the trispectrum, the 4-point. So that is to say that even beyond having no primordial non-Gaussianity in the universe, in the lambda CDM model, we don't have any non-Gaussianity. This problem, this idea could induce some non-Gaussianity in the CMB. And this is important because Planck constrains non-Gaussianity to be very, very small, if not zero. And these theories could inject energy inhomogeneously and induce this non-Gaussian signature without any constraint until we look at this data and see that we have to rule out some of these ideas. So I'm going to talk about what type of ideas give you this inhomogeneous energy injection. I want to emphasize that the homogeneous idea of perturbing recombination is the basis of many constraints on some of these models here. But we're trying to extend it to the inhomogeneous idea and see if it's even more constraining and see what we can find there. So let's talk about inhomogeneous energy injection. EI, short for energy injection. So if we have some dark matter that's interacting with the standard model, this will necessarily inject energy or affect the standard model inhomogeneously. And this is just due to the fact that you have dark matter energy injection. We know that dark matter has density perturbation just through lambda CDM. And so if you have, for example, annihilation, your energy injection rate is going to be proportional to this squared, as far as the inhomogeneous aspect of it goes. And if you have primordial black holes or you have decay, this of course is going to be dependent on just delta CDM itself. But in any case, we know that dark matter has density perturbation that's growing. This will necessarily, if it has any interaction with the standard model, will inject energy, if you have these types of theories, into the plasma inhomogeneously. But it turns out, of course, we know that this delta CDM is quite small. It grows later and later. But near recombination, delta CDM is actually too small. Is small during recombination, which is the window with which we're trying to observe the CMB in this case. So there's another idea that could produce inhomogeneous energy injection, and that's specific to accreting primordial black holes. So with accreting primordial black holes, not only does it have this type of inhomogeneity, because it's a dark matter candidate, but it also has a dependence on the relative velocity between relative velocity, VBC, where VBC is the relative velocity between baryons and cold dark matter. If you have a primordial black hole that's in the solar mass range of like 1 to 10,000 or so, if this black hole is propagating through its plasma and accreting it, it actually becomes less efficient in accreting it. So this is something that should work for any type of accretion model. It's definitely going to be dependent on the relative velocity. This relative velocity is also an inhomogeneous parameter sourced from the curvature perturbation, primordial curvature perturbation. Now, one interesting thing is if let's take the most simple model of accretion, which is spherical accretion or Bondi accretion. Let's also assume that the luminosity coming from these accreting primordial black holes is from free luminosity, or rather the plasma right next to the black hole is all ionized and interacting, causing some radiation. If you have these types of assumptions going into this problem, it turns out that the luminosity is proportional to this relative velocity inversely, very strongly. And how it's proportional is VBC over the speed of sound squared to the -3. So the speed of sound is just the speed of sound of the plasma that it's accreting, effectively, and luminosity is heavily dependent on it. And just to give you some numbers of what these are during recombination, the RMS of the relative velocity is approximately 30 kilometers per second near recombination. The speed of sound of the plasma near and after recombination is approximately 6 kilometers per second. So what you're seeing is that you have a 5 times greater relative velocity than the speed of sound, and therefore luminosity is actually going to be very heavily suppressed unless you're in like a small tail region of the distribution of relative velocity. And so to draw a quick picture of what that kind of looks like and why it's so inhomogeneous is if you populated a slice, so this is going to be like X and Y, if you generated a slice of just relative velocities, so some Gaussian random field, which is the relative velocities, you computed the luminosity with this functional dependence, what you'll find is that you'll have very small islands just scattered in this Gaussian random field of very, very high luminosity, where the luminosity of these little islands, this is in space, is 100 times greater than the mean of the luminosity. So you can see from this picture, from this functional relation, that you're going to have a very, very strong inhomogeneous energy injection from these like islands. And to give you a scale, this is about like a couple tens of megaparsecs, 10 to 100 megaparsecs between these islands. And so this is a problem that Yasin and I worked on, and we published a paper talking about this late last year, where we considered, okay, if we have these islands and we're injecting very, very high energy photons, it turns out with very, very high energy photons, they can propagate very, very far before depositing their energy. And if that's the case, then we need to consider if they propagate too far, then you're actually just going to average out all the inhomogeneous signature that you have from these primordial black holes if the photons diffuse too far. It's just essentially like a diffusion problem. And so this paper, we did some radiation transport simulations. We considered the microphysics of electrons, a lot of astrophysics, etc., to compute the distance, essentially the suppression distance from photon propagation of this inhomogeneous signal. We found that scales up to K of 0.1 inverse megaparsecs are suppressed. But even with this suppression, we actually still find that the perturbed recombination from primordial black holes, the RMS of that perturbed recombination, so now because we have these primordial black holes that are inhomogeneous, they're producing free electron fraction that's dependent on space. And the RMS of this value is actually comparable to the global effect, the mean over all space and time. of the change from primordial black holes. Now, why that's significant is that this mean effect is what's been used to constrain accreting primordial black holes. And so there's this other part of the problem that hasn't been considered, which is the RMS, or rather the spatial fluctuations, or rather the spatial inhomogeneity of this energy injection. And it's comparable to the signal that's constraining the previous, or that's giving us the previous constraints. So this is a great motivation to then, the perturbing recombination is not the observable. We have to compute how this perturbing recombination propagates to the CMB. And that's a whole other hard problem that I'm going to talk about. So finally, we're kind of going back to this picture on how the CMB is generated from this recombination. And I'm going to talk about it a little bit more mathematically and how we go about solving it. So now I'm going to talk about CMB. How you generally solve the CMB, going from some recombination to the CMB, is generally solved through the Boltzmann-Einstein differential system. Boltzmann-Einstein equations. And what these equations are really saying, it's essentially like the fluid equations, a little bit more generalized, where you are evolving some particle distribution function from some initial conditions to today. For example, this particle distribution function could be theta, which is the temperature anisotropy. So we're talking about the time derivative, or the conformal time derivative, which I won't go into detail with, of theta, which is dependent on the direction of propagation, space, and of time, which we're using eta as the time parameter. Now, how this temperature anisotropy changes is through collisions. And so on the right-hand side of this equation, we're going to have essentially the scattering rate of Thomson with photons with electrons multiplied.
So sorry, how can temperature depend on direction? Temperature is a function of position by definition, I would think.
So temperature in the sense that you're looking at a photon coming from this direction, you measure this temperature, and as opposed to this direction. So this is like temperature anisotropy. This comes from, generally, you have some distribution of photons. And
this is some moment of the distribution function.
Yeah, so yeah, you assume that it's a black body, and then you perturb, so some black body has some temperature. I'm trying to remember the distribution now. It's something like this.
No, but I mean the formal definition of this theta, it is some moment of the distribution function, no?
This theta?
Yeah.
Yes, it's related to it. When you say moment, you're talking about like integrating.
Integral the energy,
yeah.
Right?
It is related to this theta. It comes from the expansion of taking the temperature of a black body, perturbing the temperature with some theta that is dependent on space, time, and momentum, etc., and then expanding that. And I think you can relate it to some moment of the particle distribution function. In any case, how that particle distribution function changes, or this temperature changes, is through Thomson scattering. So we have some scattering rate and some linear collision operator, which encapsulates all the geometry and the changes of the photon temperature from Thomson scattering. Now, this is the general equation that's solved for finding the power spectrum of the CMB. And it's actually pretty difficult to solve. And so to answer your question a little bit, this is kind of solved by going to first order perturbation, where first order implies that you're going to first order in the curvature perturbation, the primordial curvature perturbation factor. And you kind of expand these. You assume that this differential scattering, or the scattering rate, is homogeneous because the collision operator is already first order. And you solve for theta given just this first order perturbation, and you can predict the power spectrum very, very well. And this is done already by codes like class. And just to emphasize that this is still actually quite difficult because you actually expand this into spherical harmonics. You end up with a hierarchy of differential equations going to L to infinity technically. And so class does a lot of tricks to actually solve this accurately enough. Now, what I'm talking about is a perturbed recombination. And what that means is I'm essentially changing the scattering rate, where the scattering rate has within it, it's a function of the free electron fraction. So if I perturbing recombination, then I can kind of think of it through perturbative expansion as just some mean tau dot with some change in the free electron fraction, which is now spatially dependent. And so this is actually going to higher order in this Boltzmann equation. This delta XC now has orders of curvature perturbation, whereas before, how this is solved, we assume that this is 0th order. This is just the global scattering rate. And so it turns out actually to solve this Boltzmann-Einstein equation with higher order is very, very difficult to solve. And so Yassine and I have been working on it, and we essentially solve it perturbatively again by just assuming that there we have the canonical 0th order temperature and isotropy that would come from class, for example, so there's no primordial black holes, plus some term that comes from primordial black holes, the first order perturbation. Essentially, we're just expanding this in terms of the perturbed quantities. So then we have the 0th order global scattering rate plus the primordial black hole perturbed scattering rate, which is dependent on space. And then multiplied by the collision operator, which also is being expanded. So Yassine and I are able to solve this through some approximations. We use something called a line of sight integral. Then we use some tight coupling approximations, etc. But once you get this theta 1, you can now compute higher order statistics on the CMB through this theory. This is something, by the way, I've been saying primordial black holes, but this is something that applies to any inhomogeneous energy injection that could come from any type of model you have. But specifically for primordial black holes, I hope everyone can see this.
Can you wrap up?
Sure, yeah, I'm ending right now. So specifically for primordial black holes, it turns out that this theta 1 is proportional to theta 0 times VBC squared. Right, this VBC relation is coming from the fact of the luminosity relation that I wrote, which means that this is proportional to the primordial curvature perturbation cubed. And the reason why that's important is that that implies that the first perturbation that you're going to see from accreting primordial black holes is going to be the trispectrum. So the first order term is going to have these 3 canonical temperature anisotropies in 1 perturbed PBH1. And so Yassine and I are working right now on computing this trispectrum and then doing some Fisher forecast to predict how constraining this can be considering accreting primordial black holes. And that's it.
Yeah.
Yeah, you stand up too.
So given there is this energy injection, does one expect to see just deviation from thermality of the CMB?
When you're talking about like spectral distortions,
Right.
Right. That's another problem that I haven't actually considered, but yes, I think there could be some spectral distortions that come from this. And also, I've actually been interested in the fact that if we have inhomogeneous energy injection, would we have inhomogeneous spectral distortions?
So is it clear that this is a leading effect compared to
Um,
distortion?
I don't think it is clear. I guess it depends. I don't think it is clear, and I was trying to consider that more with these very high energy photons. there might be, like, after they scatter so much, there's gonna be some bath of photons that are low energy that could actually distort the CMB. And so, yeah, I'm interested in that project as well, but no, I haven't.
So, so you say you can impose the bounds through the charge fraction, so which one will be stronger, the charge fraction?
So for accreting primordial black holes, because of this dependence on the primordial curvature, it turns out with that dependence, the bispectrum of the same thing. You asked about the bispectrum, right?
Yeah, which one's stronger?
Right. So this will actually be 0
Oh, okay.
because of just Gaussian random fields, and you'll have an odd number of Gaussian random fields, and so it'll be 0. But this is not true for another general dark matter energy injection. This is just true for primordial black holes. So this should be quite constraining, or well, obviously more constraining than 0.
But naively, just for the vanilla decaying or annihilating dark matter, it would be weaker than.
So for that naive decay and annihilation, I think I wrote here. No, not here. Oh, right here. No, yeah. For that, your inhomogeneity is coming from this term, which is just really small during recombination. Another question that I'm kind of considering is, obviously this becomes a lot bigger after recombination, and maybe during like 21 centimeter. And so I was thinking that maybe this inhomogeneous energy injection could affect the 21 centimeter. But yeah, so I think during recombination, there was a paper on this by Dvorkin, Cora Dvorkin, and some others that found that this is still just too small for recombination.
Do you have isocurvature perturbations that are larger? Could you get some effect from the injection then?
So, Nanoom, you do isocurvature perturbation stuff, right?
Yeah, but it's kind of different. So in my second project, we considered isocurvature perturbation on very small scale. In that case, we can change the background recombination history because so we look at very small scale, smaller than observable scale of CMB. So if we average over the small scale, there will be additional contribution to recombination rate that will contribute to the background recombination history. But yeah, that's
So like if I had like a crazy model, like where there's two species of dark matter and have isocurvature perturbations, and then one of them annihilates copiously with itself, or whatever, you can kind of like fill in the yada yada yada. And so you've got much larger isocurvature, but all in the dark sector, but then it's self-annihilating. Could you get some?
So yeah, I guess I would have to just look at the numbers of like what the amplification of the annihilation is, or the inhomogeneous aspect of that annihilation during recombination. But if it's greater than this, then yeah, there's no reason for it not to. Once we kind of finish this project, there's no reason that it shouldn't.
Which means like a self-dominant fraction of dark matter, right? Because isocurvature perturbations for all dark matter, right?
No, I'm imagining I've got two species of dark matter. I mean, I'm just talking like making stuff up to them.
So together they're adiabatic.
And
but
together adiabatic, but upward, downward fluctuation,
yeah.
and then some self-annihilation of one particular species or something. I mean, I'm trying to like design a model specifically to do this, but I'm just wondering if.
So yeah, that would be constrainable, I guess. Yeah. I guess as long as your isocurvature has also the cross correlation with the adiabatic modes. To the lowest order term is going to have 3 standard fields plus the perturbation. Otherwise, you're going to have to go to parametrically to higher order, right? What's this? Design it.
Any final questions for Nanoom and Trey?
I think I missed the transition from luminosity being suppressed because of the high number to why you get high luminosity islands.
Right. So this is, I mean, it's kind of hard to go from this picture to this picture. Like you kind of just have to generate a relative velocity field and plug it in. But it's really just because it's such a steep function of relative velocity that if you are slightly above the speed of sound, which we generally are considering this RMS value, if you're slightly above it, you see that you're getting this huge to the 6th power suppression. So you have to be in a very small, so if you have like some Gaussian distribution of relative velocity, you have to be in a very, very low tail of the relative velocity. Otherwise, you get this really strong 6th power suppression. And so because you're in that small tail, then you're just going to get really small islands.
can talk more over coffee. Let's thank Nanoom and Trey. There should be some caffeine and cookies.
Untitled Chapter, the third, the conversion.